So in this video, we're going to do some extra examples using permutations and combinations. Now, sometimes you see examples involving cards. So when they say they're using a standard deck of 52 cards, what this means is that there's 4 suits. So we call them diamonds, hearts, clubs, and spades. Each of them have 13 cards, and that's one of each of the 13 ranks. So that's ace, so the 1, 2, 3 up until 10, and then jack, queen, king. So each one of these ranks occurs exactly once of each suit. Okay, so in order to have a card, just draw you a card over here, we need to have a rank. Okay, so maybe it's the queen, and we need a suit. So maybe it's the hearts. Okay, so you need to know both of those things in order to know what cards you have. Now maybe I should also write hearts and diamonds are red, whereas spades and clubs, those suits are black. Okay, so this is not a course learning objective, so if there is an example or a question involving cards, obviously you're welcome to ask if you forget how many cards there are or how many of each suit, etc., etc. But just keep in mind that unless it says otherwise, this is the deck you should be imagining. So let's do a couple examples involving the cards. So in how many ways can you be dealt a 5-card poker hand from a deck of 52 distinct cards? So each of the cards is different in this deck. So there's 52 different objects. Okay, so different cards, and we want 5 of them for our hand. Now the thing that we need to imagine is, does the order we select the cards matter? So if you think about playing a game of cards, well, at least for poker, you pick up, when you say a hand, you imagine picking it up. So you can rearrange your cards in your hand. So the word hand sort of implies that the order doesn't matter. Okay, so the order they're dealt doesn't make a difference. You get the same hand no matter what. So how many of these are there? Well, this is a combination because we have 52 different objects, and we want to select 5 different objects. No repetition. Okay, so we can't have the same card multiple times. So this is going to be 52 choose 5, which, if you compute that, is 2,598,960 different hands. Now, how many of these hands have exactly 2 red and 3 black cards? So here we want to be more specific. So there's going to be 26 red cards and 26 black cards. So remember, there's 13 of each suit, and 2 of the suits are red and 2 of the suits are black. So 52, half of the deck is red and half the deck is black. So that's 26 each. And for the red ones, we want 2. And for the black ones, we want 3. And the order doesn't matter. So in order to make our hand, we have to do 2 steps. Okay, so we're going to select our red cards, and then we select our black cards. So the number of ways to select our red cards is going to be 26 choose 2. And then, so because we're doing both of these things to make our hand, I want to multiply, so I'm using the multiplication principle. And then from the black cards, we want to select 3. So if you compute each of these, it's going to be 325 times 2600, which is going to be 845,000 different hands that have 2 red and 3 black cards. Okay, let's try something different. 4 people go out for brunch to a restaurant that has 8 different items on their menu. How many different orders are possible, assuming each person orders one item? But notice it doesn't say they have to order different items, so it could be that each person orders the same item. So we have 8 menu items. Okay, and we have 4 people ordering. So do we want to pick 4 of the menu items? Not necessarily, because it's possible that everyone orders the same one. So here we need to allow repetition. So what that means is that actually we're not using a permutation or a combination here. We actually can just use the multiplication principle. So here's person 1, 2, 3, and 4, and we just want them to order. So how many options does person 1 have to order? Well, they can order any of the 8 things. Person 2 can also order any of the 8 items, etc. So I get 8 to the power 4, which is 4,096 different orders. So because of this because we're allowing the repetition here, we're not using a permutation or a combination. So remember, with those, they both require distinct items, and then you're selecting distinct items from that set of items. Okay, so from these, we had distinct menu items, but the ones we wanted to select didn't have to be distinct, and that's where the problem came from. Okay, now what about how many different orders if everyone must order a different item? Okay, so here they have to order a different item. So there's 8 menu items, and because there's 4 people and they're all ordering something different, we're going to want 4 of these items, because we're going to need 4 different dishes for them. So now we want to think, does the order matter? So I like to think about, if we were to choose the items, what that would do is it would select 4 of the items from the menu, and we would put those items on the server's tray. But when she went to the table, she wouldn't know where to put which item. She wouldn't know who ordered what. Okay, so the fact that she has to place them on the table for each person means that the order does matter. So who orders which item makes a difference. So the order, you could think about this as the order we select the items matters. So this is actually a permutation. So it's 8 permute 4. And remember that you could also think about this, which maybe will help, as 8 choose 4. So this will select 4 items for the server's tray. Okay, and this is the number, 4 factorial is arranging them to each people. So this is the number of ways server can give out the food on her tray. Oops, tray. Okay, so you can think about it either way. Now, if you compute this number, which I didn't really leave myself room for anymore, 8 permute 4 is 1,680. So that one can be confusing. But yeah, I do like to think about it when you choose them, that just puts them on the tray for the server. And then when they go to the table, they need to be able to give them to the people at the table. And this is where the ordering happens. Okay, another example. An orchestra has 9 violinists, 7 cellists, and 3 bassists. In how many ways can we form a quartet? So that's 4 people, if we have exactly 2 violinists and 1 of each of the other types. So to make our quartet, we might we want to pick violinist, cellist, and a bassist. So for the violinist, we actually want 2 here. So there's 9 violinists, and we want to select 2. Now, does the order matter? So we have to do all of these things to make a quartet. So we're doing the multiplication principle. So does the order we pick the violinist matter? So here it won't, because they're both going in the quartet. If they were playing different pieces, and we wanted to know who was playing which piece, then the order would matter. But here they're just forming a quartet, so they just have to be in the group. So the order doesn't matter. So this is going to be 9, choose 2. The cellist, you're picking 1, so you could say 7 options, or some people prefer to write 7, choose 1, because you're selecting 1 of the cellists, and then 3, choose 1 for 1 of the bassists. So this is 36 times 7 times 3, which is 756 different quartets. Now, I just want to make a note here, because often people want to do 4 spaces. So this is violinist 1, violinist 2, cellist, bassist. So they pick 1 of the violinists, so there's 9 options, and then they pick another violinist, 8 options, because you can't pick the same person, a cellist, and then a bassist, have 7 and then 3 options. If you multiply these numbers, now I should have done this in advance, but if you multiply these numbers, you get 1,512. So this is double the number above. So why is this one overcounting? Okay, so the only thing that's different is this part here. So does 9 times 8 equal 9 choose 2? Okay, well it doesn't, but what it does equal, so 9 times 8 is actually 9 permute 2. So by picking the violinists separately, so at separate times, what you've done is ordered their selection. So remember, when you're doing the multiplication principle, every time you break it up, you're saying and then. So I'm going to choose a violinist, and then I'm going to choose another violinist. So that's giving some ordering to it. And because they're just going in the group, we don't want that ordering. Okay, so this is overcounts, or sometimes we say it double counts, because here it's exactly double the other number. But this is probably the best wrong answer, as I like to say, because it's on the right track, but you've ordered something that you didn't really want ordered. So that is very common to do, which is why I wanted to emphasize it here and why it doesn't work. Okay, let's try another one. So you have all your textbooks in a bin, and you have 4 math textbooks, 5 novels for your English class, and 3 biology textbooks. So that's 4 plus 5 plus 3 is 12 books altogether. In how many ways can you arrange 3 of these books on your nightstand? So you don't care which books. Okay, so there's 12 books, and you want 3 different ones, and you want to arrange them so the order matters. Okay, so this number is going to be 12 permute 3, okay, which is 1,320. Now, in how many ways can you select 3 books to move to your nightstand? So this word select implies that you're not ordering them. Okay, so you don't care about the order, you just want to pick them. So it's similar up top, so you still have 12 books, you still want 3, but here the order doesn't matter. So we have 12 distinct books, we want 3 distinct books, so this is a combination. So it's going to be 12, choose 3, which is 220. Okay, now suppose you select one book of each type. Okay, so you already have one math book. Okay, so let's just call it, you have an M, you have an E for your English book, and you have a B for your biology book. You have one of each. And you want to arrange these on your nightstand. So you already know what these are. You don't have to pick them. You already selected them. So arrange means that order matters. Okay, so here we have 3 books, and we want all 3 arranged. So you could use a permutation, so 3 permute 3, but this is actually the same as the factorial, so it's 3 factorial. So there's going to be 6 ways to do this. So why is it a factorial? Because we had 3 books and we wanted to pick all 3 of them. So remember, the permutation allows us to pick some of them, but when we want to pick all of them, that's the exact same as a factorial. So either way. Or you could have written 3 times 2 times 1. Now, suppose you want to select 5 books from the bin. Okay, so here you want to select them. So here's you already selected them. Here you want to select them. Okay, so you want 5 books, and you want exactly 3 math and 2 novels. Okay, so we have 4 math and 5 novels for your English class. I think it was 5 novels. Okay, so for the math, we want 3, and for the novels, we want 2. Now it asks for selections. How many selections will have this? So that word implies not ordered. Okay, so when you're just selecting something, you don't care about what order you selected. So here we can do it in 2 steps. So we have our multiplication principle. We're going to select our math books, and then we're going to select our novels. So because order doesn't matter, I'm going to do 4, choose 3, and then times 5, choose 2. So this is going to be 4 times 10. So there's going to be 40 selections that have exactly 3 math textbooks and 2 novels. Okay, now the last one is a bit tricky. So again, we want to select 5 books from the bin, and we want to know in how many ways can they be arranged. So the order does matter here. Ordered. Okay, but we want alphabetical order. So we actually want a specific order. Okay, so we want, that makes things a bit different. Okay, so we don't want to count every possible order. We want one specific order. So what if, oops. So before we actually start doing this one, what if we already had the 5 books? Okay, how many ways could we put them in alphabetical order? So we already have 5 books. Okay, and we want to put them in alphabetical order. So imagine you're alphabetizing your books. They have to go from A to Z, right? There's only one way to alphabetize. So here, once we know what books they are, there's only one way to put them in alphabetical order. Okay, so now we've reduced the problem, we just need to select them. So how many ways are there to select 5 books? So remember that we have 12 books in total, and when we use the word select, we don't want them ordered, so this is going to be a combination. So there's 12 books, and we want 5 of them. So there's 12 choose 5 ways to select the books, And then after that, there's only one way to order them. So the number of ways to put them in alphabetical order, we could do it as 2 steps. Okay, so select books and then order them. Okay, now here we don't want all possible orders. We want one correct order. So there's 12, choose 5 ways to select them, and then once we have them, only one way to order them. So once we have them, there's only one way to order them, and 12, choose 5. Oh, we didn't do that. 12, choose 5 is 792. So there's that many ways to select 5 books and then put them in alphabetical order. So that was some examples of permutations and combinations. Hopefully you start getting the hang of when to use which, but it's very challenging at the beginning, so don't be discouraged if you're finding it difficult.